Need to expose custom Python functions to AI models like their native tools? We'll create a FastMCP server that turns a simple dice roller into an AI-callable tool, then connect it to OpenAI's Responses API. You'll see exactly how to define the tool, deploy the server, and make the AI use it, all in under 20 lines of code.
Import random. From FastMCP, import FastMCP. MCP equals FastMCP. Name equals dice roller. At MCP, tool. Def roll dice, end dice, int list int. Roll end dice, 6-sided dice and return the results. Return random, randint 16 for in range end dice. If name equals main. MCP, run transport equals HTTP, port equals 8000.
This demonstrates the AI tool exposure pattern, where Python functions become remotely callable endpoints for AI systems. The decorator-based approach transforms ordinary functions into typed, self-describing tools that AI models can discover and invoke. What makes this distinctive is the seamless bridge between native Python logic and AI workflows, without requiring API boilerplate or protocol expertise. The pattern works by treating decorated functions as first-class tool definitions, with type hints serving as the contract. The framework handles discovery, serialization, and transport automatically, while your code remains pure business logic. This separation of concerns lets you focus on functionality, while the system manages how those functions are exposed and consumed by AI clients. This approach matters because it solves the integration complexity problem for AI-augmented systems. Instead of building custom APIs or adapters, you define tools as native Python, and the framework handles the RPC layer. It's particularly valuable for rapid prototyping, microservices, or any scenario where you need to expose backend logic to AI systems without writing transport code or maintaining separate API definitions. The trade-off is framework dependency, but the productivity gain for AI integrations is substantial. Let's break it down line by line.
Import random.
Imports Python's built-in random module for generating pseudorandom numbers. This provides the randint function used later to simulate dice rolls with uniform distribution.
From FastMCP, import FastMCP.
This imports FastMCP, the core framework for building AI-callable tools. It transforms Python functions into structured APIs that AI models can invoke directly, handling serialization, validation, and transport automatically.
MCP equals FastMCP. Name equals dice roller.
This initializes the FastMCP instance, the core controller for AI-callable tools. The name parameter identifies this toolset in logs and the AI interface, enabling clear debugging and tool discovery.
At MCP, tool. Def roll dice, end dice, int list int. Roll end dice, 6-sided dice and return the results.
This decorator exposes roll dice as an AI-callable tool through FastMCP. The type hints and docstring automatically generate the tool's schema, defining input validation and documentation in one place.
Return random, randint 16 for in range end dice.
This is a list comprehension that generates end dice random integers between 1 and 6. It efficiently replaces a manual loop, creating the dice roll results in a single readable line. The underscore signals we only care about iteration count, not the loop variable itself.
If name equals main.
This is Python's standard entry point guard. It ensures the server only starts when the script runs directly, not when imported as a module. Without it, importing this file would automatically launch the FastMCP server.
MCP, run transport equals HTTP, port equals 8000.
This launches the FastMCP server on port 8000 using HTTP transport. The server exposes all decorated tools as AI-callable endpoints, handling serialization and request routing automatically. Standard entry point pattern for FastMCP applications. FastMCP tool exposure pattern. That MCP tool decorator transforms ordinary Python functions into AI-accessible endpoints, with automatic schema generation handling type hints and docstrings as the contract. Transport configuration in MCP. Run determines whether your server communicates via HTTP, SDDIO, or SSE, but the tool definition remains identical across all transports. This single decorator pattern bridges the gap between local Python logic and distributed AI systems without framework lock-in.
The decorator that names the tool becomes nameless to the client.